So hello dear students. So now in this subunit we are going to discuss an interesting phenomena known as successive disintegration, in which a nucleus disintegrates into the final daughter nucleus through number of steps, and in each step the intermediate nuclei that is produced is also radioactive. So it further decays into another nucleus which is again radioactive, and after number of steps it reaches finally a stable nucleus. So this basically is a form of successive disintegration in which a nucleus is converting into the final stable form into a number of multiple steps in between. Each step is also unstable and has got a lifetime or a decay constant which is different from the parent. So we are going to discuss this phenomena in a little detail in this particular subunit. So what is successive disintegration? So it is just a sequential nuclear decay process in which an unstable nucleus undergoes multiple decays, one after another, until a stable nucleus is formed. This is a common phenomenon in radioactive decay chains, especially amongst heavy elements like uranium and thorium. So in nuclear physics, successive disintegration involving a series of nuclear transformation, each can be either alpha decay or a beta decay, with each daughter nucleus formed in a decay which is also radioactive and undergoes further decay. So this process continues until a stable or a non-radioactive nucleus is produced. So what are the key components in this successive disintegration? Number one is the parent nucleus, which is the original radioactive nucleus which starts the chain. So the parent nucleus is the nucleus that is having some concentration at time t is equal to 0, and it starts the disintegration, and so it is the first or the initial end of the chain. Second is the daughter nucleus. These are the intermediate products of the decay which may be stable or radioactive. If radioactive, then they become parent for the next decay and the chain continues. And then there are different types of decay modes, as you already know. Either the decay can take place in the form of an alpha decay, which is an emission of helium nucleus, or a beta decay, which is beta minus or beta plus, which is transformation of a neutron into a proton, or vice versa, with an electron or a positron emission. And then third one is the gamma decay, which is the emission of high energy photons. Decay constant is the probability per unit time that the nucleus will decay. As I have told you in the earlier chapter, decay constant tells us what is the activity. The activity is large or small, it all depends upon the decay constant. But each element of the chain, different isotopes successively that are forming one after another, they are all having different decay constants. So they are not having the same decay constant. They are also not decaying by the same mode. The mode is also different. The decay mode is different, as well as the decay constant is also very different sometimes. So now we talk about the mathematical formulation. So consider a chain in which a nucleus A1 converts into a nucleus A2, and then A2 further converts into A3, and successively, and finally we get An, which is the final nucleus. Then NIT be the number of nuclei of type AI. So within a chain, if you randomly select one particular nuclei, then Ni of T, that is the number of nuclei of type AI, would be given as Ni of T at time t, and lambda I would be the decay constant for that particular nucleus AI. So let us Now write the equation for the first nucleus A1. So what is the decay of the first nucleus? So the A1 is decaying into A2. So the equation is dN1 by dt is equal to minus lambda 1 N1. Because A1 is the starting or the foremost parent nucleus, its decay would depend only on the concentration of itself. So the decay, the dN by dt, dN1 by dt of the first nucleus would only be proportional to the concentration N1 of the first nucleus. So its solution is simple. N1 of t is nothing but N1 of 0, that is the concentration of the first nucleus at time t is equal to 0 into exponential minus lambda 1t. So this is the solution of this particular differential equation. Now we'll write the second nucleus, the equation for the second nucleus. Now dN2 by dt is, now what is happening? This dN2 by dt gives us the rate of change of the second nucleus in the chain with respect to time. So it is forming and as well as it is decaying. It is forming from A1 and it is decaying to A3. So it is actually increasing due to the decay of A1 but also decreasing due to its decay to A3. So there are two terms here, lambda 1 N1, which tells us that the A2 is increasing by this much amount because the decay, the formation of A2 is just equal to the decay of A1. The number of atoms or number of nuclei that are decaying for A1 would be the same as the number of nuclei that are forming for A2. So this term lambda 1 N1 tells us the formation of nucleus A2 due to the decay of A1. And minus lambda 2 N2 tells us the decay of A2 to A3, which is dependent upon the decay constant of A2, lambda 2. So this is a simple equation that tells us with two terms here. First term tells us the formation of A2 from A1 and the second term tells us the decay of A2 to A3, and now the dN2 by dt is given by this equation. So this is a non-homogeneous differential equation. So the solution is not trivial. The solution takes into account both the production of A2 by decay of A1 and the loss of it by its own decay. So the general solution for A2 is given by this N2 of t, that is the number of nuclei of A2 at time t is equal to lambda 1 into N1 at time 0 divided by lambda 2 minus lambda 1 into exponential minus lambda 1 t minus exponential minus lambda 2 t. So basically this is the solution for this particular equation. As you can see, if you substitute the solution in this equation, you will see that this solution satisfies this equation. Similarly, if you continue the chain further, if you want to find out A3 and A4, it involves increasingly complex recursive differential equation and the solutions are even more complicated. So we will take a very simple example. Now a simple decay example that we are taking consists of three terms only, that is N1 is changing to N2 and then N2 is changing to N3. So basically only three members are there in the chain. N1 is the number of atoms of the parent nucleide, N2 is the number of atoms of the daughter nucleide, and N3 is the number of atoms of the stable end product. Lambda 1 is the decay constant of the parent nucleide, lambda 2 is the decay constant of the daughter nucleide, and lambda 3 is not required because N3 is not decaying at all. So it is a stable, so the lambda 3 for this is not relevant in this particular equation. So now dN by dt, dN1 by dt is given by minus lambda 1 N1, as I have told you earlier. dN2 by dt, again as I have told you in the previous slide, is lambda 1 N1 minus lambda 2 N2. And what about dN by d3? basically dn3 by dt is simply equal to lambda 2 n2, because lambda 2 n2 is the decay of n2 with respect to time. So the formation of n3 is just equal to the decay of n2. So dn3 by dt is nothing but equal to lambda 2 n2. These are called the Bateman equation because they were first solved by Bateman, and he gave the general solution for successive disintegration to n order of magnitude or n order of sequence. Solution of the Bateman equation is not very trivial, it is complicated, but you can solve it starting from the assumption that at time t is equal to 0, n2 and n3, the concentration of nuclide 2 and nuclide 3 are 0, only nuclide 1 are present, and their concentration at time t is equal to 0 is represented by n10. And the other initial number of daughter products are 0. So considering that n20 is 0 and n30 is also 0, the solutions are given by these three equations. So this again requires certain order of magnitude of mathematical complexity to solve these problems, but you can simply substitute these solutions into these equations to see that these solutions actually satisfy these three equations. So simply substitute for n1 in equation 1, substitute for n2 in equation 2, and substitute for n3 in equation 3, and you will find that these equations are satisfied by these solutions. Now you can see n1 is obviously decreasing with time because n1 is decaying into n2. What about n2? n2 is also forming and also decaying. Some of it is forming through the decay of n1 and some of it is decaying to the daughter nucleus n3. So it can either increase, it can grow, or it can actually decrease depending upon the relative magnitude of the two processes. So simply if you differentiate dn2 with dt and equate it to 0, you will find the maxima. At what time t do we have the maximum number of n2? So you just differentiate n2t by n with respect to t and equate it to 0, the first differential of n2 with respect to time, and you equate it to 0, and you will get the point at which you will get the maximum number of n2. So this I leave you as an exercise to do. Now we talk about radioactive equilibrium. So I'm going to discuss it quite briefly. Now what I have just told you in the previous subunit, as you can see, there are cases when you have what you call nuclei which are successively disintegrating one after another, and if the parent is long-lived compared to the short-lived daughter, that is, the half-life of parent is much greater than the half-life of daughter, then there can be a possibility of a secular equilibrium. So the half-life of parent is much larger than half-life of daughter, or you can in reverse say that the decay constant of nucleus 1 or the parent nucleus is much smaller than the decay constant of the daughter nucleus. So after sufficiently long time, the activity of the daughter nucleus becomes equal to the activity of the parent. So this is intuitively quite obvious that if T12 of the parent is much larger than T12 of the daughter, then after some time A2 will become equal to A1. So in that case, the number of daughter atoms N2 is proportional to the number of parent atoms. That means N1 and N2 are going to change with time, but in a proportionate manner. So the actual equation is N2 is equal to N1 into lambda 1 divided by lambda 2. So this equation we will discuss in a little detail when we are talking about, when we'll do the problems. But you can see N2 lambda 2 is equal to N1 lambda 1. This is the basic this is what the basic equation conveys. Basically, this is what this equation conveys, that n2 lambda 2 is equal to n1 lambda 1, and this is nothing but this restatement of the fact that a2 is equal to a1, because n2 lambda 2 is equal to a2 and n1 lambda 1 is equal to a1. So when the secular equilibrium is established, the activity of the parent as well as the daughter becomes almost equal, but it happens after a sufficiently long time. But there is another type of equilibrium which is called the transient equilibrium, and that is happening when the half-life of the parent is longer than that of daughter, but not by a very large factor. That is, T half of parent is greater than T half of daughter, but not much greater than the T half of daughter, as in the case of secular equilibrium. Or lambda 1 is less than lambda 2, but not much less than lambda 2, as in the case of secular equilibrium. In that case, what happens is the activity of the daughter eventually becomes proportional to the activity of the parent, but not necessarily equal. So in each case, activity either becomes equal in the first case, but in the second case it becomes proportional, but not necessarily equal, and the ratio of the activity remains constant over time in the case of transient equilibrium. So these are two very important concepts which are used quite often when we are talking about radioactive decay series, when we are talking about different elements forming one after another with different lifetimes and different half-lives and different decay constants. Sometimes it does happen that the parent is having a very large lifetime compared to the daughter, and in that case a kind of equilibrium is reached at a very later stage, at a very large time, when the concentration of the parent becomes almost equal to the concentration of the daughter in the case of secular equilibrium, in the case of proportional to the daughter in the case of secular equilibrium, and in the case of transient equilibrium the activity becomes proportional. So in the case of secular equilibrium the number becomes proportional, and in the case of transient equilibrium it is the activity that becomes proportional. So here I show, in one case I'm talking about two different scenarios. In the first scenario, in which no equilibrium is reached, in which the parent decay constant lambda 1 is larger than the daughter decay constant lambda 2, in that case, since lambda 1 is much greater than lambda 2, the parent nucleus decay very fast and becomes almost zero, whereas lambda 2 is smaller. So what happens is the daughter nucleus first grows, and then after reaching a maximum it starts decaying. So in this case T1 was 1 hour and T2 was 5 hours, and you see the Tm, that is the maximum concentration that is reached at Tm, is given by the exercise that I have given you. If you do that exercise, you will be able to get the T maxima by differentiating N2 with respect to time, and of course after this, differentiating it with respect to time, you equate the first derivative equal to 0, you will get the value of Tm. This I leave you as an exercise. In the second case, which you can see is a kind of a transient equilibrium, in which lambda 1 is less than lambda 2, N1 decreases but slowly, not as fast as in the first case, because you can see lambda 1 is less than lambda 2, whereas N2 increases, and then after reaching a maximum value it starts decreasing. And since in this case it's the reverse, T2 is 1 hour and T1 is 5 hours, that is the half-life of the daughter is 1 hour and the half-life of the parent is 5 hours. Now what is happening after a very long time, that is around 8 to 10 hours, you can see that the decay is almost proportional. So whatever decay is taking place proportionally for T1, for N1, proportionally for N2 also, the same kind of decay is taking place, and the ratio is not changing. So almost a kind of equilibrium is reached in this case. So the second figure shows a kind of transient equilibrium in the case when lambda 1 is less than lambda 2. Now we talk about real world examples. So the most common decay chain that is most extensively studied is the uranium-238 decay chain. So it starts with uranium, and after successive alpha and beta decays, it reaches the lead-206, which is stable. So each intermediate product in this chain has its own half-life and decay mode. So you can see in this graph where we plot atomic number versus number of neutrons. That is, each particular nucleus has got an atomic number as well as a specific neutron number. So for each particular nucleus, you have on the y-axis the neutron number, and on the x-axis you have the atomic number. So you start with uranium-238. So in this decay series, on the left with the green arrow is the alpha decay, which converts uranium or any particular nucleus. It takes you backward 2 steps. The Z number decreases by 2 units, and the red arrow, which is representing a beta decay, actually shifts the nucleus right by 1 step. So uranium-238 changes into thorium-234 by alpha decay. So the atomic number or the Z number decreases by 2 units, and the uranium shifts left by 2 steps. Now thorium converts into Pa-234, and what is happening, it is doing it via beta decay. So basically the atomic number increases by 1 unit, and so this nuclei shifts or jumps to the next nucleus by shifting to the right by 1 step. So when you just continue this series, you will see different successive elements that are being produced by either alpha decay or beta decay, and finally at the end you have lead-206 as the final stable product. Now we talk about these decay series. What are the applications of these decay series that we can think about, or we can actually, which are used or which are applied in the real world? So there is the radiometric dating, that is uranium-lead dating for the decay series of uranium-238. Then the nuclear reactor design, environmental monitoring, and medical physics. So we will discuss briefly all these 4 applications. First of all, what is radiometric dating? So basically uranium-238 decay series will end in the stable lead-206. So in any material, if you measure the ratio of the parent and the daughter new isotopes and knowing their half-lives, you can very precisely measure or calculate the age of that sample. If you have different isotopes, which are the successive steps of a decay series, and you precisely know the concentration of those isotopes, and also you know the half-lives, you can with a very great precision find out the age of that sample by using the value of the half-life. So since you know the half-life, you know at the start what was the concentration. If you know the concentration now, you can extrapolate it to time t is equal to 0, and from there you can find out what was the concentration at time t is equal to 0, and you can also find out at time t is equal to 0 what is the difference from time t is equal to 0 to the present time. So what is the time difference between the two? You can find out by using the simple equations of radioactivity. Now next is the nuclear reactor design. In nuclear reactor design, what is happening is any nuclear reactor produces lot of radioisotopes, and those radioisotopes are undergoing successive disintegration. So fission products that are produced in the nuclear reactor produces different isotopes with different radioactive series, and engineers can use the decay chain data to design reactor cores or different other design purpose of the nuclear reactor, because different parts of the nuclear reactor would be radioactive and would be undergoing different radioactive decay series or decay chain. And in that case, if you know the decay chain in one particular material, from there you can tell us what would be the design of that reactor core, what would be the material that would be required to make that reactor core more effective for a particular application. Also for the safe storage of the radioactive waste also. Similarly, in environmental monitoring, if you know radioactive contamination, if something happens like after a nuclear accident or in the vicinity of a uranium mine, something happens and you monitor the radioactive decay chain of different uh, elements, then you can find out from there how much radiation has penetrated inside the environment and what is the spread of the contamination that is taking place of the radioactivity that has been produced due to this accident or contamination. Similarly, medical physics also, there is a huge application of this decay series. Radioisotopes used in medical diagnostics and therapy may decay through chains. So different radioisotopes which are used in either diagnostic purpose or for therapy, they are not actually singly decaying into a stable nucleus, but they actually decay into different chains, one after another. So if you know the radioactive chain data, then from there you can design the best application for imaging or therapeutic properties. So understanding this decay path ensures optimal timing and safety in medical applications. So if you know the decay chain and the different concentrations and also the half-lives of different isotopes, you know at what time the activity is going to increase and at what time it's going to decrease. So you know the optimal timing and the optimal dosage that has to be given so that the radiation does not increase beyond its limit so that it harms the body, and it gives you the desired application or the desired radiation for the desired time so that that particular application or that particular therapy can be continued and can be uh, to the desired efficacy uh, 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 it can be done. So these are the basic you can say in the nutshell, these are the applications of radioactive decay chains. And so with this knowledge, you know what is a decay chain and also you know how it is applied and what are the uses and application of these particular decay chains, how you can apply the knowledge of nuclear physics to different fields which are relevant to the human society in general.